Okay, so this is chapter 1, section 1, so 1.1, and it is on the practice of statistics. The section primarily covers terminology that we often use in statistics. And the simplest one is population. Simplest ones are population and a sample. Then we have a parameter and a statistic. So let me just explain what a population and a sample are. So the population is simply any object of interest, and the population would contain a set of individuals. So a large set of individuals or entities. So I could call the entire state of Florida as a population because every single individual, a Floridian, would form an individual of that population. I could call the Everglades as a population, and the individual of interest could be alligators in the Everglades. So any large set of individuals or entities is what we call a population. And a sample is a set of observations chosen from each individual in the population. So I've mentioned that the population is the large set of individuals or entities, and the example that I used for the population was Florida, as the entire state is a population, and the Everglades is also a population. So if we are studying or trying to get information about Floridians, then the population would be Florida. If we're trying to say get information about alligators, for instance, in Florida, especially in Everglades, then the population would simply be the Everglades. The sample would be the set of observations that we select or measure from each of those individuals in that population. So a random sample of 20 Floridians will be a sample relating to my Florida example over here. And similarly, a random sample of 32 alligators in the Everglades. So that is also a random sample because we're observing 32 alligators, and they are chosen from the Everglades because we are interested in the Everglades. So that is our population. Now, we have a population and we have a sample, but we'd like to know about a specific quantity of interest from the population. So let's just say I'm interested in the average weight of a Floridian. So that is one thing that I would like to know about a Floridian. So how much do they weigh? And going back to the Everglades example, let's say I would want to know the average length of an alligator. Perhaps I have to be specific here, an adult alligator. So that is also a specific quantity that I'm interested in. So that entity, the numerical summary that I'm looking for an individual from a population, is what we call the parameter. So the parameter is simply a it is a numerical quantity of interest from the population for an individual entity. So in the first example, the average weight of a Floridian would be a parameter. The average length of an adult alligator for the alligator example, Everglades example, would be a parameter. Now, there is no way, it is not possible for us to go and observe every single Floridian and assess their weight to get the average. And it is not possible for us to observe every single adult alligator in the Everglades to get the average length. So what do? We have a random sample, a simple sample of 20 Floridians. We can make use of these 20 Floridians and get their weights, take the average, and that is going to give an estimated value for the average weight of a Floridian. Likewise, I could go look at those 32 adult alligators, measure their lengths, take the average, and that is going to give us an average length for an adult alligator in the Everglades. So what is a statistic? It is simply an estimated value for the parameter that we obtain using the sample. As I mentioned earlier, if I look at those 20 Floridians as long as they are randomly selected and record their weight, take the average. That is going to give us information about the average weight of a Floridian. So that is an estimate for that parameter. Likewise, if I go look at those 32 adult alligators randomly selected from the Everglades, measure their length, take their average, and I'm going to get the average length of an adult alligator in the Everglades. But both of these are estimates, because if I looked at 30 Floridians, I'm going to get a slightly different answer. If I looked at 64 alligators, I'm going to get a slightly different answer. So changing the sample is going to change the estimated value or change the value of the statistic, which is why we call it an estimate. So the next topic of interest is the type of data. So what is data? Data and sample are one and the same thing. So sample some like to call it data, some like to call it sample. It's up to you. I like to use the words interchangeably. So when we perform statistical analysis, we are trying to learn something about the population. So whatever quantity that we are trying to infer about from the population will depend on the type of data that we collect. So in a broad scheme of things, we could classify data into two types. The first one is qualitative or categorical data. So the key word here, qualitative, the key word for that is quality. If you look at categorical, the key word there is category. So qualitative variables or categorical data variables are samples or data that contain measurements that are qualities or attributes or categories of some sort. So the observations here each observation that we collect from an individual is a quality or a category of some sort. Now, a good example for this would be hair color. So if I went and picked 10 individuals or 15 individuals and I recorded their hair color, I can't give a number because we don't measure hair color using a number in practice. Rather, I may record it as black, brown, red, gray. So those are the levels of measurement that I'm going to use for hair color. The type of car a person has. Now, the type of car is not a numerical quantity. It is rather a quality or a category. So It could be a sedan. It could be a truck. It could be a van. It could be a coupe. So all of those are the levels of measurement that we would use to measure the type of car. So in the first case, there are 4 levels of measurement. And it is the same for the type of car as well. The second type is quantitative data. So quantitative data is a case where observations correspond to numerical measurements. The key word here is quantity. Well, quantity, anytime we say quantity, we're saying, oh, we're measuring something using some scale. So if you have a sample, and if every single observation in the sample is a numerical measurement, whatever sample that you have is a quantitative sample. When we have quantitative data, we can classify it furthermore into 2 types: discrete and continuous. Discrete type data are data where the observations are integers or whole numbers or discrete values. Continuous data, on the other hand, is a case where observations are real numbers. For example, the number of pets in a household. We cannot have 1.5 pets. So it's either 1 or 2. So that would be a discrete variable. The number of cans of soda an adult consumes per day. So note, I didn't use fluid ounces. I didn't use a specific measurement. I simply said a can of soda. So you may drink part of the can, but you still picked a can out. So I'm looking at discrete number of cans. So we're not going to have 1.5 cans. So you pick a can of soda, you drink the entire can of soda. But that's kind of a fuzzy example. Continuous, on the other hand, I could have the amount of butter in a croissant in grams. Now, does every single croissant have the same amount of butter? No, it is going to vary from one croissant to another. So if we take some 20 or 30 croissants and measure the butter in each of them, then those values wouldn't be whole numbers. Scientifically, one might say 1.2 grams, the other might say 2.3 grams, and so forth, which is why that is continuous. So an easier example would also be the height of an individual or the weight of an individual. Both of them are continuous. Even though when someone asks us, well, what is your weight? I'd simply say 162, but mathematically, a proper measurement would rather be 162.5 or 162.4, which is why that type of data is an example for continuous data. Measurement levels, as I mentioned back here, for hair color, type of car, and so forth, are quite important, especially in the field of psychology and sociology. Now, if we consider the type of car or hair color, both of those examples do not have a natural ordering. In the sense, I'm not going to say, oh, brown is better than black or gray is better than red. So there is no natural ordering whatsoever. And the same with the type of car. There is no natural ordering. So since there is no ordering in a categorical variable, we call that a nominal level of measurement. But if you have a categorical variable and it has a natural ordering, then we call it an ordinal level of measurement. So what are some good examples? let's say fuel efficiency of a car. And we want to give it a rating. And the rating I'm going to give would be low, medium, high, and very high. So when I look at those 4 levels, I could see a natural ordering. It goes from low to high, even though, or low to very high, even though it is a categorical variable. So there is a natural ordering, so we call it ordinal. Similarly, we can consider the example of a letter grade. A letter grade, we have F, D, C, B, and A. Even though those are numerical, those are categorical levels, those levels have a natural ordering. They move from the lowest value, which is F, all the way up to the highest value, A. The size of drink with a meal. You may either get a small or medium or large. So size of drink that a person buys with a meal is a categorical variable, but there is a natural ordering in the levels that we measure. So that's what we call an ordinal level of measurement. So nominal and ordinal levels come into play with qualitative data. When we go to quantitative data, we have two different levels. The first one is interval. The other is ratio. So when is interval level of measurement important? Interval levels are typically used to specify ranges. For example, how about a SAT score example? Now I could say 300 to 350, and I could have 600 to 650. Now, both of them have a difference of 50. 350 minus 300 is 50. 650 minus 600 is also 50. But having a SAT score in the range 300 to 350 is not the same as having a SAT score in the range 600 to 650. So interval levels are levels where the range is quite important, and two different ranges would actually mean two different values or two different quantities. The ratio level is simply the quantities that are measured as a ratio. A good example, let's say someone conducts a study and they want to assess the ratio of the weight of a Granny Smith apple to weight of a Fuji apple. And if that number happens to be 1.7 for the most part, we can conclude that the Granny Smith apple is typically 1.7 times the weight of a Fuji apple. So that particular variable is measured in a ratio level. And it's usually, or it is commonly used in the sciences. But if we take pH measurements in chemistry, that is not a ratio variable. In other words, so if we take a liquid that has a pH of 3 to another which has a pH of 6, which gives us 3/6, which is 0.5, it doesn't imply directly that one is twice as acidic as the other. By all means, it's not a linear relationship between a solution that has a pH of 3 and a one that has a pH of 6. So a ratio variable is only useful, or a ratio level of measurement is only useful when we have something called an absolute zero. An absolute zero simply implies that when we say zero, that there is no value attached to that variable. And in an interval level, though, we could have no absolute zeros. We don't have to include zero whatsoever. Another thing that we need to know about interval levels is that we can typically go for additions and subtractions with intervals. We will not be taking divisions or multiplications. What do I mean by that? With the SAT score, when I used my example, I simply stated the difference between 300 and 350, 600 and 650. So I took the difference and I concluded that the difference is 50. So you can do additions, you can do subtraction with interval levels of measurements. It's meaningful. When it comes to ratio, we usually go for division or multiplication. It wouldn't make sense for us to add or subtract with variables that are measured in ratio levels. A key thing to note here is typically the levels of measurement is not of concern in statistics, at least in the quantitative case. With the qualitative case, it is always best to understand the difference between nominal and ordinal levels. But with the quantitative case, oftentimes it wouldn't make any sense for us to classify data as either interval level or ratio level. Okay, so here are a set of examples, and we want to determine whether the underlying value is a parameter or a statistic. So the average score for a class of 28 students taking a calculus midterm exam was 72%. So if we break this down, we can see that we have a sample . The sample had 28 students. And what value did we get from those 28 students? So we calculated the average score on a calculus midterm exam. That is the quantity of interest, and that amount happened to be 72%. So the underlying value is the statistic. So what is the parameter? The parameter is simply the average score on a calculus midterm exam. That is the quantity of interest that we were interested in, and we got an estimate for that particular value, which is the parameter, and that estimated value is 72%. And where did we get that value from? We got it from the sample of 28 students. So we have 12 men who have walked on the moon, and the average time they spent on the moon was 43.92 hours. So I can break this problem down as to what the parameter is. Parameter is the quantity of interest. What were we interested in? The average time. Takes men to walk on the moon. And what is the sample? The sample would be the 12 men who walked on the moon. And what did the sample give us? The sample gave us a value of 43.92 hours. So that is simply the statistic. So in the batting average problem, we do not have a sample. A sample is a collection of observations, but we are only talking about Ty Cobb. And the value that Ty Cobb has is 0.366. We know the exact value. So in this case, 0.366 is a parameter because it is a known quantity for Ty Cobb's batting average based on his career. And also another way to look at it is to go back and look at the previous problems. We had 28 students that gave 72%. We had 12 men and the average time was 43.92. So we had a sample, and that sample gave us a value, therefore we call them statistic. The same problem, if this were to be worded as we looked at 300 or 33 games that Ty Cobb played, and using those 33 games, we ended up getting a value of 0.366. Then in that case, 0.366 would be a statistic, so, because it is a value estimated from those 33 games. Here, it is a known quantity. We don't have a sample. Therefore, it is just a direct value of the parameter. So in this problem, we have a survey. What did the survey give us? The survey gave us a sample, and that had a certain number of respondents. And we do not know the number of respondents from that survey, but what we do know is 9.6% of those responded that they used illicit drugs. of course, the number of respondents aged 12 to 17. So that bit of information, 9.6%, was obtained from the sample that we had collected from the survey. So 9.6% here is a statistic. So always remember that in order to call a quantity as a statistic, we must have a sample of observations collected from a population and use that sample to compute the value of the statistic. So these problems, we have to determine the population and the sample. So a quality control manager randomly selects 50 bottles of Coca-Cola that were filled on October 15 to assess the calibration of the filling machine. So what do we have here? Do we have a sample or do we have a population? So he selects 50 bottles to assess the calibration of the filling machine. So there was a bigger set. So those are the bottles filled on October 15, and he picks a subset of 15 bottles, or 50 bottles. So those 50 bottles would form the sample. Okay, so the next one, a farmer is interested in the weight of his soybean crop. A farmer interested in the weight of his soybean crop randomly samples 100 plants and weighs the soybeans on each plant. So it is the same thing as the previous problem. So this is a problem where I can actually support the parameter also. What is the farmer interested in? The farmer is interested in the weight of the soybean crop. And he collects 100 plants, so he is sampling 100 plants. So 100 plants from his farm would result in 100 weights for each crop. So that entirely would form the sample. Oops. So the community college is noticing that there is an increasing number of full-time students who are working while attending school. They wanted to verify this, or they wanted to get information about this, so they randomly select 128 students and ask them how many hours they work. So asking them the number of hours they work would give us information about whether the number of hours went up, down, or if it stayed the same. So the full-time students at the community college would be our population. The 128 students we picked would be the sample. What were they interested in? The administration was interested in the number of hours per week a student works, and perhaps, so that would become the parameter. It's not specified in this problem, but perhaps this sample gave us a number of, say, 24.34 as an average. That would be the statistic. Again, it's not specified. I'm just using it as an example. Hypothetically speaking, if the sample of 128 students gave us a value of 24.34 hours per week, then that would be the statistic, and that would answer the question, the number of hours per week a student works, which happens to be our parameter. So this should be full-time working students.
So if they had, for instance.
Okay, so here is a data set, and we want to identify the individual, the variable, the data corresponding to the variables, and determine if they are qualitative, continuous, or discrete. So what is the individual here? So we are looking at driver's license laws for various states. So we look at 5 different states. So each state would become an individual. And what would the variables be? The first one is the minimum age for driver's license, unrestricted. So we are classifying it as 17, 18, 16, 18. We're not using any decimal values, which is why we say unrestricted. So that would be a discrete variable. The mandatory belt use seating positions. You can see that we don't measure this numerically, rather we measure it in terms of levels. So this would be categorical or qualitative, and it has 2 levels of measurement. Front is one, all is the other, and there is no natural ordering between front and all, so we would simply call this a nominal level of measurement. And maximum allowable speed limit. So again, these are fixed values. We're not using decimal values here. So since we are looking at these 5 states, and each of them has exactly 70 or 75 or 65, this would be classified as discrete. It is the maximum allowable speed limit. But could we call it continuous? Again, it is going to depend on how the question is formulated, or how we interpret the problem. If they say, okay, the state of Alabama would allow up to 70.24, then that would be continuous. But that isn't what we're saying. We're looking at discrete values, 70, 75, and so forth. In the next table, we have 4 different variables. And the first one is the model of a BMW car. And they are measured in 6 levels: the 3 series, the 5 series, 6 series, 7 series, X3, and Z4. So the first one is categorical, and it has 6 nominal levels. So the body style here, we have coupe, sedan, roadster coupe, sport utility. It looks like there are 1, 2, 3, 4, 5 unique levels. So that is categorical. With 5 nominal levels. Now, weight in pounds. Even though there aren't any decimal values, it is sort of on a continuous scale. It is not like the previous problem where we had a fixed set of values that kept repeating. So in other words, we had 70, 75, 70, 70, and 65. Here, weight has a broader range. It goes all the way from 3,362 all the way up to 4,564. So here, weight is a continuous random variable. And lastly, the number of seats. We can't have 2.5 seats. We can't have 1.5 seats. And based on what we see, we have 4 seats, 5, 5, or 2, and so forth. So the last one would be discrete. Okay, so this is a problem that is talking about government waste, and they conducted a survey of 1,017 American adults aged 18 years or older. It's right there. The respondents were asked, of every tax dollar that goes to the federal government in Washington, D.C., how many cents of each dollar would you say are wasted? So that is the question of interest. And of the 1,017 individuals, 35% indicated 51 cents or more is wasted. So Gallup reported that 35% of all adult Americans 18 years or older believe the federal government wastes at least 51 cents of each dollar spent, with a margin of error of 4% and 95% level of confidence. Now, what is the objective of the research? The objective here is quite simple. How many cents of each dollar is the federal government wasting from your tax? That's what they wanted to know. So the amount So that is what we are interested in. That is what we are analyzing. Now, the verbiage might be different. Some people might word it differently. The wording doesn't matter here. What matters is the concept. Now, what is the population? The population of interest here is the United States. What are we interested in? We are looking at the United States, and we want to get information from individuals in the United States. And so the bigger quantity of interest would be America. And what is the sample? The sample would be the 117 American adults. (18 years or older). And they want to list the descriptive statistics. So we have two bits of information. So the first bit of information is that 35% indicated that 51 cents or more is wasted. So the first statistic is the percent of people. So what percent of people believe that 51 cents or more is wasted? So the first descriptive statistic is the 35% that we have. The second is the amount that's wasted. The amount that is wasted is 51 cents or more. So that would be the second descriptive statistic. Now, lastly, we want to know, well, what can we infer from this survey? Well, what can we infer? Well, we can infer that if we take all adult Americans, 18 years or older, 35% of them believe that 51 cents or more of each dollar is wasted by the federal government. Now, note something very, very important in the very last statement. That is our inference bit. So let me shade that or highlight it in a different color. And that is the inference part of things. Why do we call it as something that is inferred from the survey? The survey only looked at 1,017 people, but whatever knowledge that we gathered from those 1,017 American adults, we have extended that knowledge to all of United States. So the inference is actually the last part, where we take the information that we got from the survey and extend it to the entire United States population.